the second time on the podcast. Professor at UT Austin, Director of the Quantum Information Center, previously a professor at MIT. Last time we talked about quantum computing. This time we talk about computation complexity, consciousness, and theories of everything. I'm recording this intro, as you may be able to tell, in a very strange room in the middle of the night. I'm not really sure how I got here or how I'm going to get out, but Hunter S. Thompson saying I think applies to today and the last few days and actually the last couple of weeks. Life should not be a journey to the grave with the intention of arriving safely in a pretty and well preserved body, but rather to skidding broadside in a cloud of smoke, thoroughly used up, totally worn out, and loudly proclaiming, wow, what a ride. So I figured whatever I'm up to here, and yes, lots of wine is involved, I'm going to have to improvise, hence this recording. Okay, quick mention of each sponsor, followed by some thoughts related to the episode. First sponsor is SimpliSafe, a home security company I use to monitor and protect my apartment. Though, of course, I'm always prepared with a fallback plan, as a man in this world must always be. Second sponsor is 8 Sleep, a mattress that cools itself, measures heart rate variability, has an app, and has given me yet another reason to look forward to sleep, including the all-important power nap. Third sponsor is Expressvpn, the VPN I've used for many years to protect my privacy on the internet. Finally, the fourth sponsor is BetterHelp, online therapy when you want to face your demons with a licensed professional, not just by doing David Goggins-like physical challenges like I seem to do on occasion. Please check out these sponsors in the description to get a discount and to support the podcast. As a side note, let me say that this is the second time I recorded a conversation outdoors. The first one was with Stephen Wolfram when it was actually sunny out. In this case, it was raining, which is why I found a covered outdoor patio. But I learned a valuable lesson, which is that raindrops can be quite loud on the hard metal surface of a patio cover. I did my best with the audio. I hope it still sounds okay to you. I'm learning, always improving. In fact, as Scott says, if you always win, then you're probably doing something wrong. To be honest, I get pretty upset with myself when I fail, small or big. But I've learned that this feeling is priceless. It can be fuel when channeled into concrete plans how to improve. So if you enjoy this thing, subscribe on YouTube, review it 5 stars on Apple Podcasts, follow on Spotify, support on Patreon, or connect with me on Twitter at LexFreedom. Now, here's my conversation with Scott Aronson. Let's start with the most absurd question, but I've read you write some fascinating stuff about it, so let's go there. Are we living in a simulation? What difference does it make to us? I mean, I'm serious. What difference? Because if we are living in a simulation, it raises the question, how real does something have to be in simulation for it to be sufficiently immersive for us humans? But I mean, even in principle, how could we ever know if we were in one, right? A perfect simulation, by definition, is something that's indistinguishable from the real thing. But we didn't say anything about perfect. It could be
No, that's right. Well, if it was an imperfect simulation, if we could hack it, find a bug in it, then that would be one thing, right? If this was like the Matrix and there was a way for me to, do flying kung fu moves or something by hacking the simulation, well then, we would have to cross that bridge when we came to it, wouldn't we? Right? I mean, at that point, it's hard to see the difference between that and just what people would ordinarily refer to as a world with miracles.
What about from a different perspective, thinking about the universe as a computation, like a program running on a computer? That's kind of a neighboring concept.
It is an interesting and reasonably well-defined question to ask: is the world computable? Does the world satisfy what we would call in CS the church Turing thesis?
Yeah.
That is, could we take any physical system and simulate it to any desired precision by a Turing machine, given the appropriate input data, right? And so far, I think the indications are pretty strong that our world does seem to satisfy the Church-Turing thesis. At least if it doesn't, then we haven't yet discovered why not. But now, does that mean that our universe is a simulation? Well, that word seems to suggest that there is some other larger universe in which it is running, right?
Right.
And the problem there is that if the simulation is perfect, then we're never going to be able to get any direct evidence about that other universe. We will only be able to see the effects of the computation that is running in this universe.
Well, let's imagine an analogy.
Mhm.
Let's imagine a PC, a personal computer, a computer. Is it possible, with the advent of artificial intelligence, for the computer to look outside of itself to understand its creator? I mean, that's a simple. Is that a ridiculous analogy?
Well, I mean, with the computers that we actually have, I mean, first of all, we all know that humans have done an imperfect job of, enforcing the abstraction boundaries of computers, right? Like you may try to confine some program to a playpen, but as soon as there's one memory allocation error in the C program, then the program has gotten out of that playpen and it can do whatever it wants. Right? This is how most hacks work.
Right.
There's viruses and worms and exploits. And you would have to imagine that an AI would be able to discover something like that. Now, of course, if we could actually discover some exploit of reality itself, then then this whole, I mean, then in some sense we wouldn't have to philosophize about this. Right, this would no longer be a metaphysical conversation.
Well,
right, this would just be.
But that's the question: is what would that hack look like?
Yeah, well, I have no idea. I mean, Peter Shor, the very famous person in quantum computing, of course, has a joke that maybe the reason why we haven't yet integrated general relativity in quantum mechanics is that the part of the universe that depends on both of them was actually left unspecified. And if we ever tried to do an experiment involving the singularity of a black hole or something like that, then the universe would just generate an overflow error or something, right? We would just crash the universe. Now, the universe has seemed to hold up pretty well for 14 billion years. Right, so my Occam's razor kind of guess has to be that it will continue to hold up. That the fact that we don't know the laws of physics governing some phenomenon is not a strong sign that probing that phenomenon is going to crash the universe, right? But of course, I could be wrong.
But do you think on the physics side of things, there's been recently a few folks, Eric Weinstein and Stephen Wolfram, that came out with a theory of everything. I think there's a history of physicists dreaming and working on the unification of all the laws of physics. Do you think it's possible that once we understand more physics, not necessarily the unification of the laws, but just understand physics more deeply at the fundamental level, we'll be able to start, I mean, part of this is humorous, but looking to see if there's any bugs in the universe that can be exploited for, traveling at not just the speed of light, but just traveling faster than our current spaceships can travel, all that kind of stuff.
Well, I mean, to travel faster than our current spaceship could travel, you wouldn't need to find any bug in the universe, right? The known laws of physics, let us go much faster, up to the speed of light, right? And, when people want to go faster than the speed of light, well, we actually know something about what that would entail, namely that, according to relativity, that seems to entail communication backwards in time. Okay, so then you have to worry about closed time-like curves and all of that stuff. So, in some sense, we sort of know the price that you have to pay for these things, right?
Under the current understanding of physics.
That's right. We can't, say that they're impossible, but we know that sort of a lot else in physics breaks, right? So, Now, regarding Eric Weinstein and Stephen Wolfram, like I wouldn't say that either of them has a theory of everything. I would say that they have ideas that they hope, could someday lead to a theory of everything.
Is that a worthy pursuit?
Well, I mean, certainly, let's say by theory of everything, we don't literally mean a theory of cats and of baseball, and but we just mean it in the more limited sense of everything. A fundamental theory of physics, right? Of all of the fundamental interactions of physics. Of course, such a theory, even after we had it, would leave the entire question of all the emergent behavior, right? To be explored. So it's only everything for a specific definition of everything. Okay, but in that sense, I would say, of course, that's worth pursuing. I mean, that is the entire program of fundamental physics, right? All of my friends who do quantum gravity, who do string theory, who do anything like that, that is what's motivating them.
Yeah, it's funny though, but I mean, Eric Weinstein talks about this. It is, I don't know much about the physics world, but I know about the AI world, and
Mm-hmm.
it is a little, it is a little bit taboo to talk about AGI, for example, on the AI side.
Mm-hmm.
So really, to talk about the big dream of the community, I would say,
Mm-hmm.
because it seems so far away, it's almost taboo to bring it up because it's seen as the kind of people that dream about creating a truly superhuman level intelligence that's really far out there. People, because we're not even close to that. And it feels like the same thing is true for the physics community.
I mean, Stephen Hawking certainly talked constantly about theory of everything, right? I mean, people, use those terms who were, some of the most respected people in the whole world of physics, right? But I mean, I think that the distinction that I would make is that people might react badly if you use the term in a way that suggests that thinking about it for 5 minutes, have come up with this major new insight about it,
Yeah,
right?
it's it's difficult. Stephen Hawking is not a great example because I think you can do whatever the heck you want when you get to that level. And I certainly see like senior faculty,
Mhm.
that at that point, that's one of the nice things about getting older
Mhm.
is you stop giving a damn.
Mhm.
But
Mhm.
community as a whole, they tend to roll their eyes very quickly at stuff that's outside the quote unquote mainstream.
Well, let me put it this way. I mean, if you ask, Ed Witten, let's say, who is, you might consider the leader of the string community, and that's, very, very mainstream in a certain sense, but he would have no hesitation in saying, of course, they're looking for a unified description of nature, of general relativity, of quantum mechanics, of all the fundamental interactions of nature, right? Now, whether people would call that a theory of everything, whether they would use that term, that might vary. Lenny Susskind would definitely have no problem telling you that, if that's what we want, right?
For me, who loves human beings and psychology, it's kind of ridiculous to say a theory that unifies the laws of physics gets you to understand everything. I would say you're not even close to understanding everything.
Yeah, right. Well, yeah. I mean, the word everything is a little ambiguous here, right? Because and then people will get into debates about reductionism versus emergentism and blah blah blah. And so, in not wanting to say theory of everything, people might just be trying to short circuit that debate and say, look, yes, we want a fundamental theory of the particles and interactions of nature.
Let me bring up the next topic that people don't want to mention, although they're getting more comfortable with it, is consciousness. You mentioned that you have a talk in consciousness that they watched 5 minutes of, but the internet connection was really bad.
Was this my talk about refuting the integrated information theory?
Yes,
which
might
was
have
a
been.
particular account of consciousness. So yeah, I think one can just show it doesn't work.
So let me.
Much harder to say what does work.
What does work?
Yeah.
So let me ask. Maybe it would be nice to comment on. You talk about also like the semi-hard problem consciousnness, or like almost hard problem, or kind of hard.
Pretty hard.
Pretty hard.
I think I call
So
it.
maybe can you talk about that their idea of the approach to modeling consciousness and why you don't find it convincing? What is it, first of all?
Okay, well, so what I call the pretty hard problem of consciousness. This is my term, although many other people have said something equivalent to this. Okay, it's just the problem of giving an account of just which physical systems are conscious and which are not, or if there are degrees of consciousness, then quantifying how conscious a given system is.
Oh, right. Awesome. So that's the pretty hard.
Yeah, that's what I mean.
That's it. I'm adopting it, and I love it. That's a good ring to it.
And so the infamous hard problem of consciousness is to explain how something like consciousness could arise at all, in a material universe, right? Or why does it ever feel like anything to experience anything, right? And so I'm trying to distinguish from that problem, right? And say, no, okay, I would merely settle for an account that could say, is a fetus conscious? If so, at which trimester? Is a dog conscious? What about frog, right?
Or even as a precondition, you take that both these things are conscious. Tell me which is more conscious.
Yeah, for example, yes. Yeah. I mean, if consciousness is some multi-dimensional vector, well, just tell me in which respects these things are conscious and in which respect they aren't, right? And and have some principled way to do it where you're not carving out exceptions for things that you like or don't like, but could somehow take a description of an arbitrary physical system and then just based on the physical properties of that system or the informational properties of how it's connected or something like that, just in principle calculate its degree of consciousness, right? I mean, this would be the kind of thing that we would need, if we wanted to address questions like, what does it take for a machine to be conscious, right? Or when should we regard AIs as being conscious? So now this IIT, this integrated information theory, which has been put forward by Julia and a bunch of his collaborators over the last decade or two. This is noteworthy, I guess, as a direct attempt to answer that question, to to address the pretty hard problem, right? And they give a criterion that's just based on how a system is connected. So it's up to you to sort of abstract the system like a brain or a microchip as a collection of components that are connected to each other by some pattern of connections, and to specify how the components can influence each other, like where the inputs go, where they affect the outputs. But then once you've specified that, then they give this quantity that they call phi, the Greek letter phi. And the definition of phi is actually changed over time. It changes from one paper to another, but in all of the variations, it involves something about what we in computer science would call graph expansion. So basically what this means is that they want, in order to get a large value of phi, it should not be possible to take your system and partition it into two components that are only weakly connected to each other. Right? So whenever we take our system and sort of try to split it up into two, then there should be lots and lots of connections going between the two components.
Okay, well, I understand what that means in a graph. Do they formalize how to construct such a graph and data structure, whatever, or is this one of the criticism I've heard you kind of say is that a lot of the very interesting specifics are usually communicated through natural language, like through words. So it's like the details aren't always.
It's true. I mean, they have nothing even resembling a derivation of this thing. Okay, so what they do is they state a whole bunch of postulates, axioms that they think that consciousness should satisfy. And then there's some verbal discussion, and then at some point phi appears, right? And this was the first thing that really made the hair stand on my neck, to be honest, because they are acting as if there's a derivation. They're acting as if you're supposed to think that this is a derivation, and there's nothing even remotely resembling a derivation. They just pull the phi out of a hat. Completely.
It's one of the key criticisms of the studio is that details are missing.
But that's not even the key criticism. That's just a side point. Okay. The core of it is that I think that that they want to say that a system is more conscious the larger its value of phi. And I think that that is obvious nonsense. Okay, as soon as you think about it for like a minute, as soon as you think about it in terms of could I construct a system that had an enormous value of phi, like even larger than the brain has, but that is just implementing an error correcting code, doing nothing that we would associate with intelligence or consciousness or any of it. The answer is yes. It is easy to do that, right? And so I wrote blog posts just making this point that yeah, it's easy to do that. Now, Tinoni's response to that was actually kind of incredible, right? I mean, I admired it in a way because instead of disputing any of it, he just bit the bullet in the sense, he was one of the most audacious bullet bitings I've ever seen in my career. Okay, he said, okay, then fine. This system that just applies this error correcting code, it's conscious. And if it has a much larger value of phi than you or me, it's much more conscious than you or me. We just have to accept what the theory says because science is not about confirming our intuitions; it's about challenging them. And this is what my theory predicts that this thing is conscious and or super duper conscious. And how are you going to prove me wrong?
So the way I would argue against your blog post is I would say, yes, sure, you're right in general, but for naturally arising systems developed through the process of evolution on Earth, this rule of the larger E being associated with more consciousness is correct.
Yeah,
so
that's not what he said at all.
Right.
Because he wants this to be completely general, right?
So we can apply it to human computers.
Yeah, I mean, the whole interest of the theory is the hope that it could be completely general, apply to aliens, to computers, to animals, coma patients, to any of it, right?
Yeah.
And so he just said, well, Scott is relying on his intuition, but I'm relying on this theory. And to me, it was almost like, are we being serious here? Okay, yes, in science we try to learn highly non-intuitive things, but what we do is we first test the theory on cases where we already know the answer, right? Like if someone had a new theory of temperature, right? Then maybe we could check that it says that boiling water is hotter than ice. And then if it says that the sun is hotter than anything you've ever experienced, then maybe we trust that extrapolation, right? But like this theory, like if it's now saying that a gigantic grid of exclusive organs can be way more conscious than a person or than any animal can be, even if it is so uniform that it might just be a blank wall, right? And so now the point is, if this theory is sort of getting wrong, the question is a blank wall, more conscious than a person, then I would say what is there for it to get right?
So right? Your sense is a blank wall is not more conscious than a human being.
Yeah, I mean, you could say that I am taking that as one of my axes. I'm saying that if a theory of consciousness is getting that wrong, then whatever it is talking about at that point, I'm not going to call it consciousness.
Well,
I'm going to use a different word.
You have to use a different word.
Yeah,
I mean, it's possible, just like with intelligence, that us humans conveniently define these very difficult to understand concepts in a very human-centric way.
That's
like
right.
The Turing test really seems to define intelligence as a thing that's human-like.
Right, but I would say that with any concept, there's like we first need to define it, right? And a definition is only a good definition if it matches what we thought we were talking about, prior to having a definition, right? And I would say that B as a definition of consciousness fails that test. That is my argument.
So okay, so let's take a further step. So you mentioned that the universe might be a Turing machine. So like it might be computation
or simulatable by one anyway.
Simulatable by one. So what's your sense about consciousness? Do you think consciousness is computation? That we don't need to go to any place outside of the computable universe to understand consciousness, to build consciousness, to measure consciousness, all those kinds of things.
I don't know. These are what have been called the vertiginous questions, right? They're the questions that you get a feeling of vertigo in thinking about them, right? I mean, I certainly feel like I am conscious in a way that is not reducible to computation, but why should you believe me, right? I mean, and if you said the same to me, then why should I believe you?
But as computer scientists,
Yeah.
I feel like a computer could achieve human level intelligence, but and that's actually a feeling and a hope. That's not a scientific belief.
Mhm.
It's just we've built up enough intuition, the same kind of intuition you use in your blog. That's what scientists do. I mean, some of it is a scientific method, but some of it is just damn good intuition.
Mhm.
I don't have a good intuition about consciousness.
Yeah, I'm not sure that anyone does or has in the 2,500 years that these things have been discussed, Lex.
But do you think we will? Like I got a chance to attend, to hear your opinion on this, but attend the Neuralink event, and one of the dreams there is to, basically push neuroscience forward, and the hope with neuroscience is that we can inspect the machinery from which all this fun stuff emerges and see, are we going to notice something special, some special sauce from which something like consciousness or cognition emerges?
Yeah, well, it's clear that we've learned an enormous amount about neuroscience. We've learned an enormous amount about computation, about machine learning, about AI, how to get it to work. We've learned an enormous amount about the underpinnings of the physical world, and from one point of view, that's like an enormous distance that we've traveled along the road to understanding consciousness. From another point of view, the distance still to be traveled on the road, maybe seems no shorter than it was at the beginning.
Yeah.
Right. So it's very hard to say. I mean, these are questions like in sort of trying to have a theory of consciousness. There's sort of a problem where it feels like it's not just that we don't know how to make progress; it's that it's hard to specify what could even count as progress, right? Because no matter what scientific theory someone proposed, someone else could come along and say, well, you've just talked about the mechanism. You haven't said anything about what breathes fire into the mechanism, what really makes there something that it's like to be it. Right? And that seems like an objection that you could always raise, no matter how much someone elucidated the details of how the brain works.
Okay, let's go Turing test and law of surprise. I have this intuition, call me crazy, but we that a machine to pass the Turing test in its full, whatever the spirit of it is, we can talk about how to formulate the perfect Turing test. That machine has to be conscious, but we at least have to. I have a very low bar of what consciousness is. I tend to think that the emulation of consciousness is as good as consciousness. So like consciousness is just a dance, a social short that is a nice, useful tool. I think it's an exercise my dad to maybe just to ask what role does consciousness play? Do you think it passes the Turing test?
Well, look, I mean, it's almost tautologically true that if we had a machine that passed the Turing test, then it would be emulating consciousness, right? So if your position is that, emulation of consciousness is consciousness, then, so, by definition, any machine that passed the Turing test would be conscious. But but I mean, that you could say that, that is just a way to rephrase the original question. Is an emulation of consciousness, necessarily conscious, right? And you can here I'm not saying anything new that hasn't been debated ad nauseum in the literature, okay? But you could imagine some very hard cases. Like imagine a machine that passed the Turing test, but that did so just by an enormous cosmological sized lookup table that just cached every possible conversation that could be had.
The old Chinese room.
But this is, I mean, the Chinese room actually would be doing some computation, at least in Searle's version, right? Here, I'm just talking about a table lookup. Okay, now it's true that for conversations of a reasonable length, this lookup table would be so enormous it wouldn't even fit in the observable universe. Okay, but supposing that you could build a big enough lookup table and then just pass the Turing test just by looking up what the person said, right? Are you going to regard that as conscious?
Okay, let me try to make this
Yeah.
formal, and then you can shut it down. I think that the emulation of something is that something if there exists in that system a black box that's full of mystery. So like,
full of mystery to whom?
To human inspectors.
So does that mean that consciousness is relative to the observer? Like, could something be conscious for us, but not conscious for an alien that understood better what was happening inside the black box?
Yes. So that if inside the black box is just a lookup table, the alien that saw that would say this is not conscious. To us, another way to phrase the black box is layers of abstraction, which make it very difficult to see the actually underlying functionality of the system. And then we observe just the abstraction, and so it looks like magic to us. But once we understand the inner machinery, it stops being magic. And so, like, that's a prerequisite is that you can't know how it works, of some part of it, because then there has to be in our human mind entry point for the magic. So that's a formal definition of this.
Yeah, well, look, I mean, I explored a view in this essay I wrote called "The Ghost in the Quantum Turing Machine" 7 years ago. That is related to that, except that I did not have consciousness be relative to the observer, right? Because I think that, if consciousness means anything, it is something that is experienced by the entity of consciousness, right? Like I don't need
financial engineering versus DA.
To tell you that you are, right? But basically, what I explored there is, are there aspects of a system like a brain that just could not be predicted, even with arbitrarily advanced future technology, because of chaos combined with quantum mechanical uncertainty, things like that. I mean, that actually could be a property of the brain, if true, that would distinguish it in a principled way, at least from any currently existing computer, not from any possible computer.
It's the product experiment. So if I gave you information that you're in the entire history of your life, basically explain away free will with a lookup table. Say that this is all predetermined. Everything you experience is already predetermined. Wouldn't that take away your consciousness? Wouldn't you yourself, wouldn't the experience of the world change for you in a way that
well, let me put it this way. If you could do like in a Greek tragedy where, you would just write down a prediction of what I'm going to do, and then maybe you put the prediction in the box, and maybe, you open it later and you show that you knew everything I was going to do, or, of course, the even creepier version would be you tell me the prediction, and then I try to falsify it, and my very effort to falsify it makes it come true. Right. Let's even forget that that version, as convenient as it is for fiction writers, right? Let's just do the version where you put the prediction into a sealed envelope, okay? But if you could reliably predict everything that I was going to do, I'm not sure that would destroy my sense of being conscious, but I think it really would destroy my sense of having free will, and much more than any philosophical conversation could possibly do that. Right? And so I think it becomes extremely interesting to ask, could such predictions be done? Even in principle, is it consistent with the laws of physics to make such predictions, to get enough data about someone that you could actually generate such predictions without having to kill them in the process, to, slice their brain up into little slivers or something?
It's theoretically possible, right?
Well, I don't know. I mean, it might be possible, but only at the cost of destroying the person, right? I mean, it depends on how low you have to go in sort of the substrate. Like if there was a nice digital abstraction layer, you could think of each neuron as a kind of transistor computing a digital function. Then you could imagine some nanorobots that would go in and would just scan the state of each transistor, of each neuron, and then, make a good enough copy, right? But if it was actually important to get down to the molecular or the atomic level, then, eventually you would be up against quantum effects. You would be up against the unclonability of quantum space. So I think it's a question of how good does the replica have to be before you're going to count it as actually a copy of you, or as being able to predict your actions.
It's a totally open question.
Yeah. And especially once we say that, well, look, maybe there's no way to make a deterministic prediction, because we know that there's noise buffeting the brain around, presumably even quantum mechanical uncertainty, affecting the sodium ion channels, for example, whether they open or close. There's no reason why over a certain time scale that shouldn't be amplified, just like we imagine happens with the weather or with any other chaotic system. So if that stuff is important, right? Then we would say, well, you can't, you're never going to be able to make an accurate enough copy. But now the hard part is, well, what if someone could make a copy that sort of no one else can tell apart from, right? It says the same kinds of things that you would have said. Maybe not exactly the same things, because we agree that there's noise, but it says the same kinds of things. And maybe you alone would say, no, I know that's not me. It doesn't share I haven't felt my consciousness reach over to that other thing. I still feel it localized in this version, right? Then why should anyone else believe you?
What are your thoughts? I'd be curious. You're a good person to ask, which is Penrose's work on consciousness, saying that there is some, with axons and so on, there might be some biological places where quantum mechanics come into play, and through that create consciousness. Yeah.
Okay, well,
familiar with this?
Of course. I read Penrose's books as a teenager. They had a huge impact on me. 5 or 6 years ago, I had the privilege to actually talk these things over with Penrose, at some length at a conference in Minnesota. And, he is, an amazing personality. I admire the fact that he was even raising such audacious questions at all. But, to answer your question, I think the first thing we need to get clear on is that he is not merely saying that quantum mechanics is relevant to consciousness, right? That would be like, that would be tame compared to what he is saying, right? He is saying that, even quantum mechanics is not good enough, right? Because if supposing, for example, that the brain were a quantum computer, that's still a computer. In fact, a quantum computer can be simulated by an ordinary computer. It might merely need exponentially more time in order to do so, right? So that's simply not Okay, so what he wants is for the brain to be a quantum gravitational, he wants the brain to be exploiting as yet unknown laws of quantum gravity. Okay, which would be uncomputable.
That's the key point.
Okay, yes. It would be literally uncomputable. And I've asked him, to clarify this, but uncomputable, even if you had an oracle for the Halting problem, or as high up as you want to go in the sort of the usual hierarchy of uncomputability. He wants to go beyond all of that. Okay, so just to be clear, if we're keeping count of how many speculations, there's probably like at least 5 or 6 of them, right? There's first of all that there is some quantum gravity theory that would involve this kind of uncomputability, right? Most people who study quantum gravity would not agree with that. They would say that what we've learned, what little we know about quantum gravity from this ADS-CFT correspondence, for example, has been very much consistent with the broad idea of nature being computable, right? But all right, but supposing that he's right about that, then what most physicists would say is that whatever new phenomena there are in quantum gravity, they might be relevant at the singularities of black holes. They might be relevant at the Big Bang. They are plainly not relevant to something like the brain, that is operating at ordinary temperatures, with ordinary chemistry, and the physics underlying the brain. They would say that we have, the fundamental physics of the brain. They would say that we've pretty much completely known for generations now, right? Because quantum field theory lets us sort of parameterize our ignorance. Right. I mean, Sean Carroll has made this case in great detail, right? That sort of whatever new effects are coming from quantum gravity, they are sort of screened off by quantum field theory, right? And this brings us to the whole idea of effective theories, right? But we have, in the standard model of elementary particles, right? We have a quantum field theory that seems totally adequate for all of the terrestrial phenomena. Right. The only things that it doesn't, explain are, well, first of all, the details of gravity. If you were to probe it, like at extremes of, curvature or at like incredibly small distances, it doesn't explain dark matter. It doesn't explain black hole singularities. Right. But these are all very exotic things, very, far removed from our life on Earth. Right. So for Penrose to be right, he needs, these phenomena to somehow affect the brain. He needs the brain to contain antennae that are sensitive to this
black hole,
to this as yet unknown physics, right? And then he needs a modification of quantum mechanics. Okay, so he needs quantum mechanics to actually be wrong. Okay, he needs what he wants is what he calls an objective reduction mechanism, or an objective collapse. So this is the idea that once quantum states get large enough, then they somehow spontaneously collapse, right? And this is an idea that lots of people have explored. There's something called the GRW proposal that tries to, say something along those lines. These are theories that actually make testable predictions, right? Which is a nice feature that they have. But the very fact that they're testable may mean that in the coming decades we may well be able to test these theories and show that they're wrong, right? We may be able to test some of Penrose's ideas, if not his ideas about consciousness, but at least his ideas about an objective collapse of quantum states, right? And people have actually, like Dick Baumeister, have actually been working to try to do these experiments. They haven't been able to do it yet to test Penrose's proposal. Okay, but Penrose would need more than just an objective collapse of quantum states, which would already be the biggest development in physics for a century since quantum mechanics itself. Okay, he would need for consciousness to somehow be able to influence the direction of the collapse, so that it wouldn't be completely random. That, your dispositions would somehow influence the quantum state to collapse more likely this way or that way. Okay. Finally, Penrose, says that all of this has to be true because because of an argument that he makes based on Gödel's incompleteness theorem. Okay. Now, like I would say, the overwhelming majority of computer scientists and mathematicians who have thought about this, I don't think that Gödel's incompleteness theorem can do what he needs it to do. Right? I don't think that argument is sound. Okay. But that is sort of the tower that you have to ascend to if you're going to go where Penrose goes.
And the intuition he uses with the incompleteness theorem is that basically that there's important stuff that's not computable.
No, it's not. It's not just that, because I mean everyone agrees that there are problems that are uncomputable, right? That's a mathematical theorem, right? But what Penrose wants to say is that for example, there are statements, given any formal system, for doing math, right? There will be true statements of arithmetic that formal system, if it's adequate for math at all, if it's consistent and so on, will not be able to prove. Famous example being the statement that system itself is consistent, right? No, good formal system can actually prove its own consistency. That can only be done from a stronger formal system, which then can't prove its own consistency, and so on forever. Okay? That's Gödel's theory. But now, why is that relevant to consciousness? Right? The idea that it might have something to do with consciousness is an old one. Gödel himself apparently thought that. Lucas thought so. I think in the '60s, and Penrose is really just sort of updating what they and others had said. I mean, the idea that Gödel's theorem could have something to do with consciousness was, in 1950 when Alan Turing wrote his article about the Turing test. He already, was writing about that as like an old and well-known idea, and as one that as a wrong one that he wanted to dispense. Okay, but the basic problem with this idea is, Penrose wants to say that, and all of his predecessors want to say that, even though this given formal system cannot prove its own consistency, we as humans, sort of looking at it from the outside, can just somehow see it. Right? And the rejoinder of that, from the very beginning has been, well, can we really? I mean, maybe he, Penrose can, but can the rest of us? Yeah. Right? I noticed that it is perfectly plausible to imagine a computer that could say, it would not be limited to working within a single formal system, right? They could say, I am now going to adopt the hypothesis that my formal system is consistent, right? And I'm now going to see what can be done from that stronger vantage point, and so on. And I'm going to add new axioms to my system. Totally plausible. There's absolutely, Gödel's theorem has nothing to say against an AI that can repeatedly add new axioms. All it says is that there is no absolute guarantee that when the AI adds new axioms, it will always be right. Okay, and that's of course the point that Penrose pounces. But the reply is obvious. And, it's one that Alan Turing made 70 years ago. I mean, we don't have an absolute guarantee that we're right when we add a new axiom. Right. We never have, and plausibly we never will.
So Alan Turing, you took part in the Loebner Prize?
Not really. No,
I
didn't. I mean, there was this kind of ridiculous claim that was made almost a decade ago about a chatbot called Eugene Goosebin.
I guess you didn't participate as a judge in the Loebner Prize.
I didn't.
But you participated as a judge in that. I guess it was an exhibition event or something like that. Or was Eugene?
Eugene Goosebin. That was just me writing a blog post because some journalists called me to ask about it.
Did you ever chat with him?
I did chat with Eugene Goosebin. I mean, if it was available on the web.
Oh, interesting. I didn't.
So yeah. So all that happened was that a bunch of journalists started writing breathless articles about first chatbot that passes the Turing test, right? And it was this thing called Eugene Goosebin that was supposed to simulate a 13-year-old boy. And apparently someone had done some test where people couldn't were less than perfect, let's say, distinguishing it from a human. And they said, well, if you look for and the answer is, well, it just kind of parries you because it doesn't know what you're talking about, right?
So just to
Yeah.
clarify exactly in which way they're obvious. They're obvious in the sense that you convert the sentences into the meaning of the objects they represent, and then do some basic obvious will mean your common sense reasoning with the objects that the sentences represent.
Right. It was not able to answer, or even intelligently respond to basic common sense questions. So let me say something stronger than that. There was a famous chatbot in the '60s called Eliza, right? That managed to actually fool, a lot of people, right? Or people would pour their hearts out into this Eliza because it simulated a therapist, right? And most of what it would do is it would just throw back at you whatever you said, right? And this turned out to be incredibly effective, right? Maybe therapists know this. This is one of their tricks, but it it really had some people convinced. But this thing was just like, I think it was literally just a few hundred lines of Lisp code, right? It was not only was it not intelligent, it wasn't especially sophisticated. It was a simple little hobbyist program. And Eugene Goosman, from what I could see, was not a significant advance compared to Eliza, right? And that was really the point I was making. And this was, you didn't, in some sense, you didn't need a computer science professor to sort of say this. Like anyone who was looking at it and who just had, an ounce of sense could have said the same thing, right?
Well,
But because, these journalists were, calling me, like the first thing I said was, well, no, I'm a quantum computing person. I'm not an AI person. You shouldn't ask me. Then they said, look, you could go here and you could try it out. I said, all right, so I'll try it out. But now, this whole discussion, I mean, it got a whole lot more interesting in just the last few months.
yeah, I'd love to hear your thoughts about GPT.
In the last few months, we've had, the world has now seen a chat engine or a text engine, I should say, called GPT-3. I think it's still, it does not pass a Turing test. There were no real claims that it passes the Turing test, right? Comes out of the group at OpenAI, and they've been relatively careful in what they've claimed about the system. But I think this as clearly as Eugene Goosman was not an advance over Eliza, it is equally clear that this is a major advance over Eliza, or really over anything that the world has seen before. This is a text engine that can come up with kind of on topic, reasonable sounding completions to just about anything that you ask. You can ask it to write a poem about topic X in the style of poet Y, and it will have a go at that. Yeah. And it will do, not a great job, not an amazing job, but a passable job. Definitely, as good as in many cases, I would say better than I would have done, right? You can ask it to write, an essay, like a student essay about pretty much any topic, and it will get something that I am pretty sure would get at least a B minus, in most, high school or even college classes, right? And, in some sense, the way that it did this, the way that it achieves this, Scott Alexander of the much mourned blog, Slate Star Codex, had a wonderful way of putting it. Said that they basically just round up the entire internet into a slurry. Okay, and and I, to tell you the truth, I had wondered for a while why nobody had tried this, right? Like, why not write a chatbot by just doing deep learning over a corpus consisting of the entire web, right? So now they finally have done that, right? And the results are very impressive. It's not clear that people can argue about whether this is truly a step toward general AI or not, but this is an amazing capability that we didn't have a few years ago. That if a few years ago, if you had told me that we would have it now, that would have surprised me. And I think that anyone who denies that is just not engaged in it. It's there.
So their model takes a large part of the internet and compresses it in a small number of parameters relative to the size basic kind of a querying mechanism, just like you described, where you specify a kind of poet and that you want to write a poem, and somehow is able to do basically a lookup on the internet of relevant things. I mean, that's what it. How else do you explain it?
Well, okay. The training involves, massive amounts of data from the internet, and actually took lots and lots of computer power, lots of electricity, right? There are some very prosaic reasons why this wasn't done earlier, right? But it cost some tens of millions of dollars, I think.
Less,
just
but,
for
approximately like a few $1 million.
Oh, okay. Oh, really? Okay.
More like 4 or 5.
Oh, all right. Thank you. I mean, as they scale it up, it will.
It'll cost, but then the hope is cost comes down, and all that kind of stuff.
But basically, it is a neural net. So what's now called a deep net, but it's basically the same thing, right? So it's a form of algorithm that people have known about for decades, right? But it is constantly trying to solve the problem, predict the next word, right? So it's just trying to predict what comes next. It's not trying to decide what it should say, what ought to be true. It's trying to predict what someone who has said all of the words up to the preceding one would say next.
Although to push back on that, that's how it's trained. But,
that's right. No,
but it's arguable
yeah,
that our very cognition could be a mechanism that's that simple.
Of course. I never said that it wasn't.
Right. But
yeah.
But,
sometimes that is, if there is a deep philosophical question that's raised by GPT-3, then that is it, right? Are we doing anything other than just predictive processing, just constantly trying to fill in a blank of what would come next after what we just said up to this point? Is that what I'm doing right now?
Is it possible? So the intuition that a lot of people have, well, look, this thing is not going to be able to reach the Everest question. Do you think it's possible that GPT 5, 6, and 7 would be able to do this exact same process to do something that looks indistinguishable to us humans from reading?
The truth is that we don't really know what the limits are, right? Because what we've seen so far is that GPT-3 was basically the same thing as GPT-2, but just with much larger network, more training time, bigger training corpus, right? And it was very noticeably better, right, than its immediate predecessor. So we don't know where you hit the ceiling, right? That's the amazing part, and maybe also the scary part, right? That now my guess would be that at some point, like, there has to be diminishing returns. Like, it can't be that simple, can it? Right.
Well,
but I wish that I had more to base that guess on.
Right. Yeah. Some people say that there would be a limitation on we're going to hit a limit on the amount of data that's on the internet.
Yeah. So sure. So there's certainly that limit. There's also like if you are looking for questions that will stump GPT-3, right, you can come up with some without, even getting it to learn how to balance parentheses, right? Like it can, it doesn't do such a great job, right? Its failures are ironic, right? Like basic arithmetic, right? And you think, isn't that what computers are supposed to be best at? Yeah. Isn't that where computers already had us beat a century ago, right? And yet that's where GPT-3 struggles, right? But it's amazing, that it's almost like a young child in that way, right? That but somehow, because it is just trying to predict what comes next, it doesn't know when it can stop doing that and start doing something very different, like some more exact logical reasoning, right? And so one is naturally led to guess that our brain sort of has some element of predictive processing, but that it's coupled to other mechanisms, right? That it's coupled to, first of all, visual reasoning, which GPT-3 also doesn't have any of, right?
Although there's some demonstration that there's a lot of promise there.
It can complete images. That's right.
And using the exact same kind of transformer mechanisms to like watch videos on YouTube, and the same self-supervised mechanism to be able to it'd be fascinating to think what kind of completions you could do.
Oh yeah, no, absolutely. Although, like, if we ask it to, like, a word problem that involves reasoning about the locations of things in space, I don't think it does such a great job on those, right? To take an example, and so the guess would be, well, humans have a lot of predictive processing, a lot of just filling in the blanks, but we also have these other mechanisms that we can couple to, or that we can sort of call as subroutines when we need to. And that maybe to go further, that one would want to integrate other forms of reasoning.
Let me go on another topic
sure.
that is amazing, which is complexity. What and then start with the most absurdly romantic question of what's the most beautiful idea in computer science or theoretical computer science to you? Like what just early on in your life or in general has captivated you and grabbed you?
I think I'm going to have to go with the idea of universality. You're really asking for the most beautiful. I mean, so universality is the idea that you put together a few simple operations, like in the case of Boolean logic, that might be the AND gate, the OR gate, the NOT gate, right? And then your first guess is, okay, this is a good start, but obviously, as I want to do more complicated things, I'm going to need more complicated building blocks to express things, right? And that was actually my guess when I first learned what programming was. I mean, when I was, an adolescent, and someone showed me Apple Basic, and then GW Basic. Anyone listening remembers that. Okay, but I thought, okay, well now, I felt like this is a revelation. It's like finding out where babies come from. It's like that level of, why didn't anyone tell me this before, right? But I thought, okay, this is just the beginning. Now I know how to write a basic program. But to, really write an interesting program, like a video game, which had always been my dream as a kid, to, create my own Nintendo games, right? But obviously I'm going to need to learn some way more complicated form of programming than that. Okay, but eventually I learned this incredible idea of universality, and that says that no, you throw in a few rules, and then you already have enough to express everything. Okay, so for example, the and, the or, and the not case can all, or in fact, even just the and not case, or even just the NAND case, for example, is already enough to express any Boolean function on any number of bits. You just have to string together enough of them.
You build a universe with NAND gates.
You can build a universe out of NAND gates. Yeah. The simple instructions of BASIC are already enough, at least in principle. If we ignore details like how much memory can be accessed and stuff like that, that is enough to express what could be expressed by any programming language whatsoever. And the way to prove that is very simple. We simply need to show that in BASIC or whatever, we can write an interpreter or a compiler for whatever other programming language we care about, like C or Java or whatever. And as soon as we had done that, then ipso facto, anything that's expressible in C or Java is also expressible in BASIC. Okay, and so this idea of universality, goes back at least to Alan Turing in the 1930s, when he wrote down this incredibly simple pared down model of a computer, the Turing machine, right? Which he pared down the instruction set to just read a symbol, write a symbol, move to the left, move to the right, halt, change your internal state, right? That's it. Okay, and anybody proved that this can simulate all kinds of other things. And so in fact today we would say, well, we would call it a Turing universal model of computation. That is, it has just the same expressive power that BASIC or Java or C++ or any of those other languages have, because anything in those other languages could be compiled down to Turing machines. Now, Turing also proved a different related thing, which is that there is a single Turing machine that can simulate any other Turing machine if you just describe that other machine on its tape, right? And likewise, there is a single Turing machine that will run any C program, if you just put it on its tape. That's a second meaning of universality.
first of all, that he could visualize it, and that was in the 30s.
Yeah,
think.
30s. That's right.
Before computers really. I mean, I don't know how. I wonder what that felt like. Learning that there's no Santa Claus or something. Because I don't know if that's empowering and paralyzing. Because it doesn't give you any. It's like you can't write a software engineering book and make that the first chapter and say we're done.
Well, right. In one sense, it was this enormous flattening of the universe.
Yeah.
Right. I had imagined that there was going to be some infinite hierarchy of more and more powerful programming languages. And then I kicked myself for having such a stupid idea. But apparently Gödel had the same conjecture in the 30s.
Oh, good.
And then
you're in good company.
Well, and then Gödel read Turing's paper and he kicked himself. He said, "Yeah, I was completely wrong about that." Okay,
yeah.
but I had thought that maybe where I can contribute will be to invent a new, more powerful programming language that lets you express things that could never be expressed in BASIC. Right, and how would you do that? Obviously, you couldn't do it itself in BASIC, right? But there is this incredible flattening that happens once you learn what is universality. But then it's also an opportunity, because it means once you know these rules, then the sky is the limit, right? Then you have kind of the same weapons at your disposal that the world's greatest programmer has. It's now all just a question of how you wield them.
Right, exactly. But so every problem is solvable, but some problems are harder than others.
And there's the question of how much time, of how hard is it to write a program, and then there's also the questions of what resources does the program need, how much time, how much memory. Those are much more complicated questions, of course, ones that we're still struggling with today.
Exactly. So you've I don't know if you created Complexity Zoo or
I did create the Complexity Zoo.
What is it? What's complexity?
Oh, all right. Complexity theory is the study of sort of the inherent resources needed to solve computational problems. Okay, so it's easiest to give an example. Let's say we want to add two numbers, right? If I want to add them, if the numbers are twice as long, then it will take me twice as long to add them, but only twice as long, right? It's no worse than that.
For a computer,
or for a person using pencil and paper, for that matter.
If you have a good algorithm.
Yeah, that's right. Even if
if
you just use the elementary school algorithm of just carrying, then it takes time that is linear in the length of the numbers, right? Now, multiplication, if you use the elementary school algorithm, is harder because you have to multiply each digit of the first number by each digit of the second one, and then deal with all the carries. So that's what we call a quadratic time algorithm, right? If the numbers become twice as long, now you need 4 times as much time. Okay, so now, as it turns out, people discovered much faster ways to multiply numbers using computers, and today we know how to multiply 2 numbers that are n digits long using a number of steps that's nearly linear in n. These are questions you can ask, but now let's think about a different thing that people they've encountered in elementary school, factoring a number. Okay, take a number and find its prime factors, right? And here, if I give you a number with 10 digits, I ask you for its prime factors. Well, maybe it's even, so you know that 2 is a factor. Maybe it ends in 0, so you know that 10 is a factor, right? But, other than a few obvious things like that, if the prime factors are all very large, then it's not clear how you even get started, right? It seems like you have to do an exhaustive search among an enormous number of factors. Now, as many people might know, for better or worse, the security, of most of the encryption that we currently use to protect the internet is based on the belief, and this is not a theorem, it's a belief that factoring is an inherently hard problem for our computers. We do know algorithms that are better than just trial division, and just trying all the possible divisors, but they are still basically exponential. Okay?
Exponential is hard.
Yeah, exactly. So the fastest algorithms that anyone has discovered at least publicly discovered. I'm assuming that the NSA doesn't know something better.
Yeah.
Okay, but they take time. It basically grows exponentially with the cube root of the size of the number that you're factoring, right? So that cube root, that's the part that takes all the cleverness. Okay, but there's still an exponential.
Right.
There's still an exponentiality there. But what that means is that, like, when people use 1,000-bit keys for their cryptography, that can probably be broken using the resources of the NSA or the world's other intelligence agencies. People have done analyses that say, with a few $100 million of computer power, they could totally do this. And if you look at the documents that Snowden released, it looks a lot like they are doing that or something like that. It would kind of be surprising if they weren't. Okay, but if that's true, then in some ways that's reassuring, because if that's the best that they can do, then that would say that they can't break 2,000-bit numbers. Right. Right. Then 2,000-bit numbers would be beyond what even they could do.
They haven't found an efficient algorithm. That's where all the worries and the concerns of quantum computing came in. That there could be some kind of shortcut around that.
Right. So complexity theory is a huge part of, let's say, the theoretical core of computer science. It started in the 60s and 70s as sort of an autonomous field. So it was already it was well developed even by the time that I was born. Okay, but I in 2002 I made a website called the Complexities Theorem to answer your question, where I just tried to catalog the different complexity classes, which are classes of problems that are solvable with different kinds of resources. Okay, so these are kind of you could think of complexity classes as like being almost to theoretical computer science, like what the elements are to chemistry, right? They're sort of they're our most basic objects in a certain way.
I feel like the elements have a characteristic to them where you can't just add an infinite number.
Well, you could, but beyond a certain point, they become unstable. Right. So it's like in theory, you can have atoms with and look. I mean, a neutron star, is a nucleus with untold billions of neutrons in it, of hadrons in it. Okay, but for sort of normal atoms, right? Probably you can't get much above 100, atomic weight 150 or so. Or sorry, I mean beyond 150 or so protons without it, very quickly fissioning. With complexity classes, well, yeah, you can have an infinity of complexity classes, but maybe there's only a finite number of them that are particularly interesting, right? Just like with anything else, you care about some more than about others.
So, what kind of interesting classes are there?
Yeah.
I mean, you can have just maybe say what are the if you take any kind of computer science class, what are the classes you learn?
Good. Let me tell you sort of the biggest ones, the ones that you would learn first. So, first of all, there is P. That's what it's called. Okay, it stands for polynomial time, and this is just a class of all of the problems that you can solve with a conventional computer, like your iPhone or your laptop. By a completely deterministic algorithm, right? Using a number of steps that grows only like the size of the input raised to some fixed power. Okay, so if your algorithm is linear time, like for adding numbers, hey, that problem is in P. If you have an algorithm that's quadratic time, like the elementary school algorithm for multiplying two numbers, that's also in P. Even if it was the size of the input to the 10th power or to the 50th power, well, that wouldn't be very good in practice. But formally, we would still count that. That would still be a P. Okay, but if your algorithm takes exponential time, meaning like if every time I add one more data point to your input, if the time that's needed by the algorithm doubles, if you need time like 2 to the power of the amount of input data, then that we call it exponential time. Okay, and that is not polynomial. Okay, so P is all of the problems that have some polynomial time algorithm. Okay, so that includes most of what we do with our computers on a day-to-day basis. all the sorting, basic arithmetic, whatever is going on in your email reader or an Angry Birds. Okay, it's always P. Then the next super important class is called NP. That stands for non-deterministic polynomial. Okay, does not stand for not polynomial, which is a common confusion. But NP is basically all of the problems where if there is a solution, then it is easy to check the solution if someone shows it to you. Okay, so actually a perfect example of a problem in NP is factoring, the one I told you about before. Like if I gave you a number with thousands of digits, and I told you that I asked you, does this have at least three non-trivial divisors, right? That might be a super hard problem to solve, right? It might take you millions of years using any algorithm that's known, at least running on our existing computers. Okay, but if I simply showed you the divisors, I said, here are three divisors of this number, then it would be very easy for you to ask your computer to just check each one and see if it works. Just divide it in, see if there's any remainder, right? And if they all go in, then you check, well, I guess there were, right? So any problem where, wherever there's a solution, there is a short witness that can be easily, like a polynomial size witness that can be checked in polynomial time. That we call an NP problem, okay? And so every problem that's in P is also an NP, right? Because, you could always just ignore the witness and just, if a problem is in P, you can just solve it yourself.
Right.
Okay, but now, in some sense, the central mystery of theoretical computer science is every NP problem in P. So if you can easily check the answer to a computational problem, does that mean that you can also easily find it?
Even though there's all these problems that appear to be very difficult to find the answer, it's still an open question whether good answer exists. So
because no one has proven that there's no way to do it.
It's arguably the most I don't know, the most famous, the most maybe interesting, maybe you disagree with that, problem in theoretical computer science. So what's your...
The most famous, for sure.
P equals NP.
Yeah.
If you were to bet all your money, where do you put your money?
That's an easy one. P is not equal to NP.
Okay, so,
I like to say that if we were physicists, we would have just declared that to be a law of nature. Just like thermodynamics.
That's hilarious.
Giving ourselves Nobel Prizes for discovery. Yeah, no. Look, if later it turned out that we were wrong, we just give ourselves more Nobel Prizes. Yeah. Because we're
so harsh, but so true.
It's really just because we are mathematicians or descended from mathematicians. We have to call things conjectures that other people would just call empirical facts or discoveries, right?
Okay, so,
but one shouldn't read more into that difference in language, about the underlying truth.
Okay, so you're a good investor and good spender of money. So then let me ask another way.
Yeah.
Is it possible at all? And what would that look like if P indeed equals NP?
Well, I do think that it's possible. In fact, when people really pressed me on my blog for what odds would I put 2 or 3% odds.
Wow, that's pretty good.
That P equals NP. Yeah, because when P, you really have to think about, like, if there were 50 mysteries like P versus NP, and if I made a guess about every single one of them, would I expect to be right 50 times? And the truthful answer is no. Okay.
Yeah.
So and that's what you really mean in saying that you have better than 98% odds for something. Okay, but there could certainly be surprises. And look, if P equals NP, well, then there would be the further question of, is the algorithm actually efficient in practice? Right? Don Knuth, who I know that you've interviewed as well, right? He likes to conjecture that P equals NP, but that the algorithm is so inefficient that it doesn't matter anyway, right? Now, I don't know. I've listened to him say that. I don't know whether he says that just because he has an actual reason for thinking it's true or just because it sounds cool.
Yeah.
Okay. But that's a logical possibility, right? The algorithm could be n to the 10,000 times, or it could even just be n squared time, but with a leading constant it could be a Google times n squared or something like that. And in that case, the fact that P equals NP, well, it would ravage the whole theory of complexity. We would have to, rebuild from the ground up. But in practical terms, it might mean very little, right? If the algorithm was too inefficient to run. If the algorithm could actually be run in practice, like if it had small enough constants, or if you could improve it to where it had small enough constants that it was efficient in practice, then that would change the world. Okay.
You think it would have what kind of impact?
Well, okay. I mean, here's an example. I mean, you could. Well, okay. Just for starters, you could break basically all of the encryption that people use to protect the internet. You could break Bitcoin and every other cryptocurrency, or mine as much Bitcoin as you want to, right? Become a super duper billionaire, right? And then plot your next move.
Right.
Okay.
That's just for starters.
Right. Now your next move might be something like, you now have like a theoretically optimal way to train any neural network, define parameters for any neural network, right? So you could now say, like, is there any small neural network that generates the entire content of Wikipedia, right? And now the question is not can you find it, the question has been reduced to does that exist or not? Yes. If it does exist, then the answer would be yes, you can find it. Okay, if you had this algorithm in your hands. Okay, you could ask your computer. I mean, P versus NP is one of these 7 problems that carries this $1 million prize from the Clay Foundation. If you solve it, and others are the Riemann hypothesis, the Poincare conjecture, which was solved, although the solver turned down the prize, right? And 4 others. But what I like to say, the way that we can see that P versus NP is the biggest of all of these questions is that if you had this fast algorithm, then you could solve all 7 of them. Okay, you just ask your computer, is there a short proof of the Riemann hypothesis, right? That a machine could, in a language where a machine could verify it, and provided that such a proof exists, then your computer finds it in a short amount of time without having to do a brute force search. Okay, so I mean, those are the stakes of what we're talking about. But I hope that also helps to give your listeners some intuition of why I and most of my colleagues would put our money on P not equal.
Is it possible? I apologize, this is a really dumb question, but is it possible the proof will come out that P equals NP, but an algorithm that makes P equals NP is impossible to find? Is that crazy?
Okay, well, if P equals NP, it would mean that there is such an algorithm.
Right? That it exists, yeah.
But it would mean that it exists. Now, in practice, normally the way that we would prove anything like that would be by finding the algorithm.
By finding one algorithm.
But there is such a thing as a non-constructive proof that an algorithm exists. This has really only reared its head, I think, a few times in the history of our field, right? But it is theoretically possible that such a thing could happen. But yeah, there are even here there are some amusing observations that one could make. So there is this famous observation of Leonid Levin, who was one of the original discoverers of NP completeness, right? And he said, "Well, consider the following algorithm that, I guarantee, will solve the NP problems efficiently, just as provided that P equals NP." Okay, here is what it does. It just runs, it enumerates every possible algorithm in a gigantic infinite list, right? From into alphabetical order, right? Yeah, and many of them maybe won't even compile, so we just ignore them. Okay, but now we just run the first algorithm, then we run the second algorithm, we run the first one a little bit more, then we run the first 3 algorithms for a while, we run the first 4 for a while. This is called dovetailing, by the way. This is a known trick in theoretical computer science. Okay, but we do it in such a way that whatever is the algorithm out there in our list that solves NP complete, the NP problem sufficiently, will eventually hit that one, right? And now the key is that whenever we hit that one, by assumption, it has to solve the problem, it has to find the solution. And once it claims to find the solution, then we can check that ourselves, right? Because these are NP problems, then we can check it. Now, this is utterly impractical, all right? you'd have to do this enormous, exhaustive search among all the algorithms. But from a certain theoretical standpoint, that is merely a constant prefactor, right?
It's at least possible.
That's merely a multiplier of your running time. So there are tricks like that one can do to say that in some sense the algorithm would have to be constructed. But in the human sense, it is possible that it's conceivable that one could prove such a thing via a non-constructive method. Is that likely? I don't think so. Right? Not personally.
So that's P and P. The complexity zoo is full of wonderful creatures.
Well, it's got
what
about
else?
500.
500. So how do you get?
More?
How do you get more? How do you,
Well, okay. I mean, just for starters, there is everything that we could do with a conventional computer with a polynomial amount of memory, okay, but possibly an exponential amount of time because we get to reuse the same memory over and over again. Okay, that is called P space. Okay, and that's actually we think an even larger class than NP. Okay, well, P is contained in NP, which is contained in P space, and we think that those containments are strict.
And the constraint there is on the memory. The memory has to grow polynomially with the size of the problem.
That's right. But in P space, we now have interesting things that were not in NP, like as a famous example, from a given position in chess, does white or black have the win? Let's say, assuming provided that the game lasts only for a reasonable number of moves. Okay, or likewise for Go. Okay, and then even for the generalizations of these games to arbitrary size boards. Because with an 8x8 board, you could say that's just a constant size problem. You just, in principle, you just solve it in O of one time, right? But so we really mean the generalizations of games to arbitrary size boards here. Or another thing in P space would be like I give you some really hard constraint satisfaction problem, like a traveling salesperson or packing boxes into the trunk of your car or something like that. And I ask not just is there a solution, which would be an NP problem, but I ask how many solutions are there. Okay, that count the number of valid solutions. That actually gives those problems lie in a complexity class called sharp P, or like it looks like hashtag P.
Got it.
Okay, which sits between NP and P space. There's all the problems that you could do in exponential time. Okay, that's called X. So, and by the way, it was proven in the 60s that X is larger than P. Okay, so we know that much. We know that there are problems that are solvable in exponential time that are not solvable in polynomial time. Okay, in fact, we know that there are problems that are solvable in n cubed time